Right, this is 7.5.5 alternating currents. Now, in direct currents, which you observe in batteries or capacitors, circuits that use these as an energy source, current flows from positive to negative. That's conventional current. Electrons, obviously, as we talked about before, go the opposite way. So in DC, which are battery or capacitor, current flows from plus to minus. So an example circuit, a very simple one, which is just a resistor connected to a cell. You've got plus and minus. Now in alternating currents, the polarity of the terminals constantly switches. So for example, in the UK, our domestic sockets have got two wires that are used to deliver electricity. It's the live wire and the neutral. The neutral is at 0 volts, and the live wire switches from plus 230 volts to minus 230 volts and back again, and it will do that 50 times every second. So it's at 50 hertz. So in AC, the terminals change polarity. So for example, if we had a similar circuit as above, so we've got here plus or minus 230 volts at 50 hertz. And we use the AC symbol, which is the wave. Would actually be beneficial if I were to shift these a little bit. Okay, not possible. I'll just rewrite it. Right, that just looks a bit better. Okay, so let's recall back to last lesson. If we're inducing an EMF using a rotating coil or a rotating magnet, we wrote down the equation that EMF was equal to ban omega sine omega t. Now ban omega, well, they're all constants. Flux density is a constant. The area of the coils is a constant. The number of turns in the coils is a constant. The angular frequency is a constant, assuming that the coils or the magnet are neither speeding up or slowing down. It's in a constant motion. So in which case, the EMF is a sine function with respect to time. The induced EMF is sinusoidal. It oscillates like a sine wave. So let's draw that. So your AC voltage comes from BAN sine omega t. So epsilon is proportional to sine omega t. I'll put that in brackets. Yes, there should be an omega here. Omega. So if we put V on the y-axis here and we put time on the x-axis, our graph would look something like this. So it just looks like a wave. So the amplitude of this wave is called the peak voltage. So this is called peak voltage, and we write that as V naught. We also have a peak to peak voltage, which is double the peak voltage. And over here would be the period, the time taken to complete one oscillation. And just like in waves, if you know the period, you know the frequency. So the frequency is equal to 1 over the period. And now we run into some issues. Say if we had a DC signal that had a potential difference of 5 volts, and we had an AC signal that had a peak voltage of 5 volts. They're not going to deliver the same energy. They're not going to do the same amount of work. Because the AC signal is not always at 5 volts. It constantly changes. It goes up, and then it goes down. And it goes up again, and then it goes down again. So we can't compare a 5 volt DC to a 5 volt peak AC. Well, okay, we're quite smart, we're physicists, so we say, right, that can be easily solved. Why don't we just take the average potential difference? Well, what's the average potential difference of a sine wave? It's 0. Because it's equally positive as it's equally negative. Half the time it's 5 volts positive, and anything between 0 and 5 volts, and equally amount of time its peak voltage is 5 volts negative, and everything else that's in between 0 and minus 5 volts. So we have to find a clever way of doing this. So we use something called the root mean square. The root mean square, when you're doing the operation to get to it, you're actually doing it the reverse way around. So first you take the equation, you square it first. Now when you square it, you're making it bigger. But you're also turning all negatives into positives. Then you take the mean, so you're averaging it. And after you've averaged it, then you square root it to bring it back down in magnitude again. So, the RMS of AC. So we start with epsilon equals 2. Tan omega sine omega t. That gives us a graph that looks something like this. Then we square it. So square the function. So that turns everything into a positive, but also makes it larger. Now we find the average of it. So take the mean of the squared function. And just to illustrate the point here, I'm going to redraw the above graph overlaid on this graph, but I'm going to draw it as a dotted line instead. I'll do my best to draw it as it was seen above. Now imagine these as piles of sand that you've got in a garden, and you basically don't want to remove any amount of sand. You want to keep the same amount of sand, the same amount of stuff, but you're going to flatten it, right? So you're just going to roll it down until it's flat. Now if you flatten that sand, its overall height would decrease, but the amount of space that the sand covers will remain the same. So it will turn into this flat line you see here. And the shaded region of the flat line, apologies, the shaded region of that flat line is the same as the shaded region of the squared function above. So it's got the same shaded area. And then finally, we square root the mean square. And just to demonstrate this, I'm going to draw the above line again. So the flattened line from above, I'm going to draw that again, but I'm going to draw it as a dotted line. And our new line is smaller. So in this one, the potential difference is called RMS voltage and is less than V0. Now, off camera, I'm going to do the derivation for this. It's not needed in A level, but there is an appreciation as to the next couple of equations I'm going to give to you. And it's a proof that these are the equations. So peak to RMS equations. So V RMS is equal to V naught over root 2. And then for the current, I RMS is equal to I naught over root 2. And it doesn't matter what kind of sine wave that alternating current was. Doesn't matter if it had a very large amplitude. It doesn't matter if the frequency was changed. No matter what you do to it, the RMS value is always the peak voltage or the peak current over root 2. And for power, so P RMS is equal to I RMS V RMS. And if we did that, we do V naught over root 2 times by I naught over root 2. So it's V naught I naught, or I naught V naught, whichever order you want to put it in, over root 2 times root 2, which is just I naught V naught over 2. In the 90s and 80s, when hi-fi systems were more popular than they are today, this became a real issue with some companies who used to advertise their speaker systems with their peak power. And if you compare that to more reputable brands at the time, who used to give their power in RMS, it was misleading for those who weren't clued on about these things, and they thought that the lesser speaker system that were giving double the amount of power were better and louder than the more reputable brands who were giving their power in terms of RMS, because you'd end up reporting half the amount of power. And the peak power is misleading as well, because you only momentarily reach that power. You're not constantly delivering that amount of power.